Okay, so this week this is the final week of your course. So I will not include other topics, new topics or topics details in this week, but one topic I have to cover because of that. If you say the signal processing course, this topic is very much important, and so I will take this one topic, not details, maybe some as in this course, maybe the introduction of these topics I will give you. Later on you can detail study on this topic, because this is another topic which is very important for your signal processing. So, that week that I will cover this week, and then I will talk about that some problem like that question paper, what kind of question paper will come in the final exam, and some problem I will solve in this class. So, this week basically a subtopic you can say, and which will cover mostly one or two lectures. And then the third lectures may be on tutorial, that around that exam, what kind of questions will come, what kind of mathematical problem you have to solve, and some problem I will present it to you and I will solve it for you, that whatever that solution will be there. So, you can get some essence of that, but mostly that final exam will be contain that numerical problem, there is no theoretical part will be there. Okay. So, let us start with that topic which I said, that is called power spectrum estimation, which is an important topic for signal processing, and there is a lot of things you have to learn. So, power spectrum estimation. So, two things was there, one is power spectrum, another one is estimation. So, problem is twofold, one is what is power spectrum, what is energy spectrum, what is spectrum of the signal, as I discussed during the class on the signal discrete Fourier transform, that how to calculate the spectrum, and then we add another word which is called estimation. So, if I able to calculate the spectrum, then why this estimation is involved, but commonly the subject, that topic is known as power spectrum estimation. So, where it is used? So, from any signal, like let's say that you are developing a sensor, the sensor produce an electrical signal, after conditioning of the signal, that signal is digitized. Now, once you digitize that signal, then what you want to detect, something you have to measure or something you want to classify from the sensor signal. So, one of the parameter we said the spectrum, yes, spectrum characterize the systems, yes, no problem, but I have to estimate the spectrum, power spectral density PSD, or estimate the spectrum. So, what do you mean by estimation of the spectrum? Where is the error? So, when it is estimation, the estimation come into the picture when there is no deterministic, something cannot be directly measured. So, I can estimate that things. So, why this estimation is come? So, the whole lectures will be discussed what is power spectrum and what is power spectrum estimation, why the word estimation is there, and if I want to estimate, then what should I do? So, let us talk about the first power spectrum. What is power spectrum? So, when I say the digital computer, to use a digital computer for spectral analysis of the signal of a continuous time series. Why I said continuous time series? Because if I say XAT is my analog signal, then once I digitize it and I get that Xn. So, Xn is nothing but a series which contain the samples, value of the sample. So, it is nothing but a time series along the timeline. So, n is the time index. So, I can say continuous t is sampled using n into t. So, n is the index, sample number 0, sample number 1, sample number 2. So, I can say this is time series. So, now what I want the spectrum of this time series. That means, you know, if I have a time domain signal, suppose I have a time domain signal XAT. So, XAT has a time domain signal. Let us say XAT equal to cos omega t. You know, it has a spectrum. Spectrum means the power across the frequency. So, this axis is power, this axis is frequency S. So, when I plot the power for different frequency, If I say cos omega t, so that there is a distinct frequency in omega, then I know the power spectrum will be two distinct frequency I get, which is one is omega omega, another is minus omega. So that I will get. That is a representation of the spectral domain of the cos omega t. So what I said that I have a power. So instead of analog signal, I have a time series x of n. Now I have to compute the spectrum of x of n. Now when we digitize XAT analog signal to digital signal, some limitation I have already there. What is the first limitation? First limitation is that Fs, sampling frequency. So I know Xn, that XAT or analog signal must be band limited signal. If it is not band limited signal, I cannot convert to digital signal. So band limited means it must have a frequency band. So let us say it is bandwidth is 0, bandwidth is B. So if I know from the Nyquist rate, Fs is equal to twice B at least. My Fs must be greater than or equal to twice B. Or on the other hand, I can say the Xn, the digital signal is a band limited signal. I do not know whether that XAT contain many frequency, but once I digitize it, I forcefully band limited it by Fs by 2. So that is called anti-aliasing filter. So when I design that analog digital converter, in the input of the analog to digital converter, I have an anti-aliasing filter, which band limited my input signal by Fs by 2. So if the XAT contains the frequency which is above Fs by 2, due to the anti-aliasing filter, I cannot get the spectrum of that signal. For example, we know we have a sound, let us say audio signal. We know it is 20 hertz to 20 kilohertz. But let us say a audio signal is sampled at 16 kilohertz. That means I am band limited the audio signal to 8 kilohertz, although it contained after 8 kilohertz component, but I cannot analyze it in the digital version of the audio signal, which is represented by Xn and sampling frequency is 16 kilohertz. So when I say input signal, when I say spectral analysis, I only can analyze the spectrum of the signal which is below Fs by 2. If the signal has any component which is greater than Fs by 2, I cannot analyze that. Okay. So that is the one limitation. The second limitation is when I do the Fourier transform. Let us say I have an Xn. How do I convert it to the frequency domain? When we compute Xk using Fourier transform, or I can say discrete Fourier transform I use to convert Xn to Xk in frequency domain. So if I know the length of the DFT is n, then I am considering the signal Xn is periodic with the n. So x of n may be infinite length, but I have to take finite length of the signal which is represented by n. So once I take the finite length of the signal, then I know the frequency component, let us say it is sampled by let us say Fs, then I know the resolution of this spectrum analysis, the frequency component I will get from k equal to 0 to n minus 1 with a frequency is equal to Fs by n. That means suppose I have a signal and sampling frequency is 16 kilohertz and n is equal to 1000, then I know that the frequency component which I will get, that the spectral resolution is nothing but a 16k divided by 1k. So it is nothing but a 16 hertz. So what will happen? So, suppose I have a 200 Hertz component in the signal, I know, but I cannot get exactly 200 Hertz component in the sampled version due to the limitation of finite length n. So, what I get every 16 Hertz. So, I cannot get, since 2000 is not divisible by 16. So, I cannot get a k value for which basically it is in 2000 Hertz. So, suppose I have a signal xat is equal to, let us say, 10 cos 2 pi 2000 t. That means analog frequency capital F is equal to 200 t, 200 Hertz. Now, if I sample this signal by 16 kilohertz, x of n I will get, and take the n point DFT n is equal to 1000, then I cannot get the exactly 200 Hertz component, because I will get k, what the k value? 200 divided by 16. So, if it is 16, then 1, 4, 40, so 12 point something. So, k equal to 12, that means 12 into 16, how much will come? 32 and 1 6. So, 2 9, so 192 Hertz. So, I will get a component at 192 Hertz, and I will get a component which is 192 plus 16. So, which is equal to around, I can say 208 Hertz. So, ideally, if I able to analyze the spectrum, I should get a component at 200 Hertz only, but due to the band limitation or due to the length, the finite length of the signal, I cannot get that exactly 200 Hertz. So, the power which exists in 200 Hertz in the signal power will be distributed among the nearby component, which is called DFT leakage. Now, once I say the finite length, then there is another problem. So, how do I get the finite length of the signal? That means I have an infinite length signal, I take a chunk of the signal which is nothing but a windowing. So, I know the frequency response of the signal is nothing but a convolution of the window frequency response and the signal frequency response. So, exact signal frequency response I cannot get once I analyze the finite length of the signal. So, when I say xn is xat equal to a cos omega t, it is nothing but a deterministic signal. Let us say non-deterministic signal, random process signal. So, in that case, I do not have that x omega t, the non-deterministic point. So, in that case, I have to estimate the non-deterministic signal spectra. Now, you may say, sir, if I increase the n, so that may come to the resolution is equal to 1 Hertz. So, once I increase the length n, what we are basically doing? If the n is very large, frequency resolution no doubtly is increased. I get the every component. Let us say I require a 1 Hertz. So, n equal to 16k in this case, 16,000. So, if the signal is in non-stationary signal is stationary signal, I can take the large signal, and if I take the large signal, computational complexity will be increased. Let us say I say the computational complexity is there, I take a large signal. But think about a non-stationary signal. If my signal is non-stationary, that means over the timeline signal is property is changed, then if I take a large window, basically I lose the time resolution. So, I increase the frequency resolution, but I lose the time resolution. So, I cannot take a large number of sample evidence. So, I have to find out the spectrum of xat or xn using the small number of evidence or sample. So, that introduce an error. So, this is the error in case of a deterministic signal. Now, say that empirical time series are inherently noisy and they are modeled as coming from stochastic process. So, deterministic signal, that means x of at is equal to a cos omega t is a deterministic signal, but generally practical all signals are non-deterministic, because there will be a signal along with some noise. Now, if I want to find out the true spectra of the signal, then due to the noise I have to estimate the power spectrum. So, the error due to the analysis is already there, error due to the windowing, error due to the finite length already there. In addition with the noise is a problem. So, I have to estimate the power, so I cannot say that determine the power spectrum of a random signal, I cannot do that. I have to estimate the power spectrum. I can say, okay, this may be the probable, the best estimation for the power spectra of the signal. So, that is why it is called power spectral estimation. Power spectral estimation. Okay. So, what is the problem? The problem, the general problem of the spectral estimation is the determine the spectral content of a wide sense stationary random process based on a finite set of observations. What I said, I have a signal in infinite length, but I cannot do that infinite length spectrum analysis, because when I say the discrete Fourier transform, the signal must be deterministic, the finite length of the signal n. So, I have to take a finite length of the signal and estimate the spectrum on the random process signal. So, the goal of the problem is determine the distribution of the signal power over the frequency for a given finite records of signal. So, what is power spectral estimation? Find out. So, suppose I give you a signal, I said what are the component exist in the frequency component exist in the signal and what are their power value. So, suppose I said vibration analysis, I am doing an accelerometer on a machine and finding out the signal. Now, what I look for? I look for a particular component, frequency component. If there is something wrong, then some particular frequency component power or range of frequency component power will be increased. So, what are you looking for? What is my problem? I have a machine, I am put an accelerometer there. So, I am collecting a signal which is XAT, time signal. Then I digitize the signal x of n using Fs. That means I am band limited the signal, okay, done. Then I want to find out, let us say, what are the frequency component power of 2000 Hertz to let us say 1 kilohertz. So, those frequency component, what is the possible power, what is the spectrum of this one? How do I measure? Because I put the accelerometer there, along the timeline signal is coming. So, how much signal I will take when I want to estimate that frequency component of 2000 to 1 kilohertz? Time is infinite. So, what I will say? I will take a determinist, I will take a finite length. So, let us say I have given finite length. Let us say I said 1 second signal I given you. From the 1 second signal, you have to estimate what are the power of the frequency component from 2000 Hertz to 1 kilohertz. So, determine the distribution of the signal power over the frequency for a given finite records of signal. I cannot get an infinite records of signal. So, that is my goal. So, x axis will be the frequency, y axis will be the power. I have to draw that spectrum. But I know when I say the finite, it introduces an error. When I say the analog to digital conversion, it introduces an error, and the signal will not only signal, there will be a noise also. So, it is not a purely deterministic signal. There will be some signal, the signal will be corrupted with noise also. So, then from the noisy signal, how do I estimate that spectrum? That is called power spectral estimation. Is it okay? So, I have defined what is power spectral estimation. So, now when I say deterministic signal, there is some application. I have already explained one application, let us say accelerometer. There is other application, hidden property, periodicity finding out the hidden periodicity of the signal. Speech processing and audio devices. We want to find out the frequency component. Let us say I want to find out whether the signal has male signal or female signal. So, I find out the fundamental frequency of the component, fundamental frequency of the signal. So, power, the fundamental frequency power will be very high. So, I find out that fundamental frequency and I calculate the male that signal. Or spectral entropy can be one parameter. Suppose I have a signal, this is a speech signal. I want to find out whether it is a caw or whether it is a saw. So, spectral features can be a parameter. So, I can say find out the spectral spectrum of the signal. From the spectrum I can easily say that whether it is a voice signal or it is a noise signal, noisy signal or the sibilant signal or fricative signal, those kind of things can be done. Medical diagnostics, very much important power spectrum. So, seismology, ground movement study, always spectrogram is nothing but a power spectrum. Have you seen that spectrogram like an X-ray plate, which I have shown you during that frequency analysis of the signal? Radar signal, sonar signal, control system, everywhere. The Border plot, what is the Border plot? The Border plot, when you make a control system, Border plot, x-axis is the frequency, y-axis is the power. So, nothing but a spectrum of the signal. So, if the signal is deterministic, then we said energy density spectrum, energy density spectrum. When I say the signal, let us say the sequence of xn is a sampling version of the continuous time signal or the sampling rate is fs, and xat is a deterministic signal. It is not a random signal, it is a deterministic signal. So, you know a signal has two types signal, one is called energy signal, another is called power signal. When the energy, so if the signal energy is finite, then I call it is an energy signal. Signal energy may be infinite, but power may be finite, then we call it is a power signal. So, when the energy is finite, that how do I calculate the signal energy? Let us say xat, t is infinite. So, I can say xat is the energy is nothing but a squaring of the signal. Now, if I say the sampled version of the xat is x of n, so it is nothing but a x of n multiplied by x of n. So, x of n square is nothing but the energy, because xat is nothing but a voltage. When I say xat, what is that? Along the time axis there is a voltage. So, you know the energy is equal to V into I. So, it is nothing but a V square by R. R is constant. So, V square means energy. So, how does the energy representation? The how much area is contained by the signal. So, if it is a digital signal, it is nothing but a square of the sample value. If it is analog signal, it is nothing but a square integrated over the minus infinity to plus infinity is the total energy. So, if the energy is finite, then the Fourier transform exists, and this is the Fourier transform for a continuous time signal. So, what is Parseval theorem? You said the energy can be computed in both the domain. It can be computed from the time domain, it can be computed from the frequency domain. So, what is Parseval theorem? Basically, what it is said? It is says that, I will take a slide here. Let us say I show you from a digital signal. Slide is in analog signal. Suppose I have a signal x of n. X of n is equal to 1, 2, 3, 4. Now, I take the discrete Fourier transform, I get x of k. What Parseval theorem says that if I compute energy in the time domain, it is nothing but a summation of square of the sample. So, it is nothing but a 1 square plus 2 square plus 3 square plus 4 square, the energy, which is equal, the same energy is contained in the spectral version of the signal also. So, what is spectral version? I know it is nothing but a k varies from this side and this side k and this side is x of mod of x of k. So, if I all frequency component amplitude if I square up, then I also get the same energy. So, I can say the x of k whole square summation over the k and here summation over the n. Energy cannot be destroyed or so this energy will be equal, that is Parseval theorem. So, in analog domain I can say this is the energy of the analog signal, this is the energy calculated from the frequency domain representation of the signal. It is nothing but the integration, analog domain it is nothing but the integration. So, this x of f whole square represent the distribution of the signal energy as a function of frequency. Then I can say this x of mod of x of m whole square, x of f whole square is called energy density spectrum of the signal. Now, when I told you, suppose I told you draw a spectrum. So, I have a signal x of n, then I take the discrete Fourier transform, I get x of k of length n. Forget about what will be the error introduced by n, how do I get that xk, all those things forget about that, first initially forget about that. So, I know xn is nothing but a voltage signal and xk is nothing but a voltage spectrum. So, I know when I want to the power or energy, I have to square it up. So, what is spectrum? Spectrum is nothing but this axis is frequency, this axis is the power. So, the power means x of k mod whole square, that is nothing but a power. So, x of k is a complex signal a plus jb. So, power is nothing but a square plus b square, root over will be off because of the square for different frequency. Now, since it is discrete domain, so the frequency is discrete, this is the k, frequency varies from k. What is the relationship between the k and analog frequency f? F is equal to fs by n into k, that I know. So, I calculate the f corresponding k and calculate the spectrum magnitude value, I get a point. So, once I for every k I will get a point, I draw that, I get the spectrum representation of x of n, that is the spectrum. Okay. So, that is the spectrum. So, that spectrum I can calculate it from the signal using discrete Fourier transform. So, what is the internal problem? Internal problem is that x of n is an infinite length signal. So, I have to make the finite duration. So, x of n is multiplied by a wn, window function. So, effect of that window will come into the spectrum. So, that introduce an error. So, since there is an error due to the window, so I have to estimate the true spectrum of x of n. That is why I call power spectral estimation. Okay. So, next class I will talk about how this autocorrelation is also involved during the power spectral estimation. Okay. Thank you.